We have arrived at section 4.7, which is about coordinatization. And the idea here is something that we've already come across several times, which is that once you specify a basis for a finite dimensional vector space, then there's a very systematic way of identifying any vector in the space with a vector in Rn. So, for instance, the way this has come up is if you have, say, a polynomial, something like this, then we have sort of several times informally identified this with a vector. So this is an element in R3, and this is an element in P2. And we've already sort of thought of these as being in some sense the same. If you do addition, you could do it either in R3 or in P2, and they sort of work the same. So now we're going to try to make this a little bit more formal and mathematically rigorous. And the first thing we need to do is that we need to order our basis. So we've already talked about what a basis is. So we start with exactly the same point. Let V be a vector space, and suppose you're given some basis ui. Then if you order these elements, you impose a specific order on them. So it's u1, u2, and then un. Then you get an ordered basis. So this is in contrast then to, so remember in a set, that's where you use the curly brackets. Then you can think of this as just a bag of elements. There's no specific order up here, but once we use the parentheses, then we think of these as ordered. So given any basis, you create an ordered basis. Then, given any vector x, we of course know that there are some unique elements b1, b2 up to bn that are the expansion coefficients of x with respect to this basis. So we know that they exist because the basis is a spanning set, and they're unique because the basis elements are linearly independent. So the bj's are uniquely defined, and together they form the vector b, which is in Rn. And we use this notation here. So we say x, and then there's a bracket around it, and then there's the basis, because these numbers, they do depend on the basis. So for a specific vector space, as we've seen, you can have several different bases. Let's revisit our very classical example here, which are quadratic polynomials. They form a vector space. We use our standard basis, and then everything gets very easy. So let's see if we can evaluate this entity. So we want to find the vector b that has these expansion coefficients, and this is very easy in this case because p is 7 times 1, it's minus 3 times x, and it's 2 times x squared. So now we just read off. 7 is b1, minus 3 is b2, and 2 is b3. So in this case, b is equal to 7 minus 3, 7 minus 3, and 2. But there is a reason that we specify the basis in this notation, and it's that if you pick a different basis, then the vector changes as well. So suppose we just modify the basis a little bit. So I form a linear combination of the first two vectors to form two other vectors. So the basis c is a little bit different than b, and now you could easily verify. I'm not going to do the computation, it's very simple, but you can of course verify that p of x is now equal to 5 times 1 plus x plus 2 times 1 minus x plus 2x squared. Let's just double check. That's 5 plus 5x plus 2 minus 2x plus 2x squared. So that seems to work. Yeah. So in this case, we find that for the vector is the same, p, but now the basis is different, and then the expansion coefficients are different as well. So the point is that this vector there is not the same as that vector there. If you pick a different basis, you get a different vector. Let's do an example in R2. So this is one of our easiest vector spaces, and now suppose that we pick a basis. So what is this basis? It's a pretty simple thing. Here is U1. Here is U2. So now I want to find C1 and C2 such that C1 U1 plus C2 U2 is equal to X. So this is a linear system that has U1 and U2 as the columns in the coefficient matrix. So now let's form the matrix U. That's the 2 by 2 matrix with columns U1 and U2. In this case, it's just 1, 1, 0, 2. Then this linear system, we could, well, we get C1, C2 is U inverse, X1, X2. And now I'm just going to write it down. What is U inverse? In this case, it is 1, 0 minus 1 half times x1, x2. Let's do an example. Suppose we take the vector 3, 1. Okay, something like that. That's x. It is 3, 1. Then what would b work out to be? So it is U inverse times 3, 1. Minus 3 halves plus. Okay, so something like that. So let's check. So 3 times U1 plus, or minus rather, U2. What does this work out to? So 3, 1, 1 minus 0, 2. 3, 3 minus 0, 2 is 3, 1, which is x. So it works. And of course, I see I drew the vector wrong. That's not the vector 3, 1. And I'll delete that. Man. Three, 1 is this vector. So I, for a second, thought that I had done this wrong, but it's that I'd drawn it wrong, so that's 3U1, and then we subtract U2, and we end up at 3, 1. So this works. Now let's consider a general case. So we are in Rn, and suppose we're given an ordered basis, U1 up through Un, and now given a vector x in Rn, I want to find its expansion coefficients, b. So we need to solve, it's exactly the same problem, it's now set in a general setting, so I want to solve this linear system star. It has a square coefficient matrix, which is the matrix, it corresponds to a linear system. With the square coefficient matrix, it's the matrix U, whose columns is formed by the vectors U1 up through Un. Because then I can write this system star as simply UB equal to X. And the solution is, of course, U inverse times B. In practice, computing the inverse of a matrix can be sort of difficult, especially if the matrix is large, and in particular if B is chosen to give you nice numbers. So in practice, it's often better to just do Gaussian elimination. You form the extended coefficient matrix like that, and then you perform row operations until you end up with identity in the left slot here, and then you get X, U inverse equal to U inverse B to the right. Now, suppose we also are given a second basis. So let C be another basis. And then we let lowercase c denote the expansion coefficients in that basis. So now the question is, given B, how do you find C? This is a very common problem. You may work with two different bases, and one basis is good for certain tasks, another one is good for other tasks. So what you want to do now is you need to solve the linear system. Let's say so B1 U1 plus up to Bn Un. So this is the system. We write this as U times B is equal to V times C. Right, so now what did we do? We formed the matrix V, whose columns are the basis elements V1 up through Vn. So now we need to solve this linear system. We can do this very straightforwardly. We find that C is equal to V inverse U times B. So if we set P to be the matrix V inverse U, then C, which are the expansion coefficients with respect to the C basis, is P times B, which are the expansion coefficients with respect to the B basis. So now we've solved the task. So we've computed this little square matrix P, that's V inverse times U. And that's how you move from one set of expansion coefficients to another one. Now let's make things even more fun, and suppose we have three bases. So we have the basis B, C, and D. And I'm being a little inconsistent with my vector notation, but now it should be right. So now we have the same question. So given a vector x, I can expand it either using the u basis, the v basis, or the w basis, and then I get these vectors b, c, and d. So in other words, these are the expansion coefficients with respect to the three different bases. So clearly we've already seen the first step here. So because Vc is equal to ub, if you solve for c, you get this expression here. And then you can of course do the second one just analogously. W times d is equal to v times c, and if you solve this for w, you get this expression here. So now you can combine them. So d is equal to w inverse times VC, and this is equal to W inverse V, B inverse U times B. So now this guy is the transition matrix to go from B to D. And you see that it works out, right? Because the V and the V inverse cancels. So you get this expression, which is exactly what you would have gotten even if you never had the C basis to begin with. So to summarize, if P is the matrix that takes you from the B expansions to the C expansions, and Q is the one that takes you from the C expansions to the D expansions, then Q times P is what takes you from the B expansions directly to the D expansions. And also you can take the inverse to go from, so you have the C and you want the B expansions, then you could alternatively solve. So if we take this same equation here and we solve for B, now we find that B is equal to U inverse V times C, which is P inverse times C, where P was V inverse U. So in other words, to go backwards, to go from B to C, you apply P, and to go from C to B, you apply P inverse. All right, so now this is getting a little bit intricate, but I think if we work some numerical examples, and in particular if you work some homework problems, this will probably become a little bit more clear. But you should be aware that this stuff is getting more theoretically involved and less computational than the material we've covered earlier in the semester. Let us revisit this issue of practical computations. So suppose we are given, so it's exactly the same problem. So given these, you're given two bases and you form the matrices U that have these guys as their columns and V that have the VI's as its columns, then how do you compute V inverse times U? And just as before, you don't really need to compute V inverse. So the main point on this slide is no need to compute V inverse. If the matrices are of size 2 by 2, you might as well, because it's so easy, but if they get bigger, and then there's a shortcut. And the trick is to note that P satisfies the equation VP is equal to U. And we can solve this by row reducing, by applying Gaussian elimination to this system. So you see here we have the coefficient matrix, and that's the right-hand side in the linear system. So now you just do all these tedious steps of row reduction and you end up with identity on the left and then V inverse times U on the right. And now you just read off. This entity here is P. Let's show with a concrete example. So this is the same basis as we had before, the U1, but now we add the second basis, which is the C1. And we want to compute the coefficient matrix P. So set U to be the matrix whose columns are the vectors U1 and U2. V is the matrix whose columns are made up by V1 and V2, like that. And then P satisfies VP is equal to U. So let's solve. Okay, now this all gets a little tedious. So you just do row reduction. I'm going a little bit fast because you've done this a million times. So what do we get? We get 7 minus 4 times 5/3. So that's 7 minus 20/3, which is 1/3. And then we get minus 1/3, and the 2 is left unchanged. We scale the second row. And then we just eliminate the 5/3 to get identity there. And then now we can just read off P. So this should be the matrix P. So let's do a quick test. See if this worked. Suppose B is equal to 3, 1. Then X is 3U1 minus U2 is equal to 3, 1. Yes. And now the claim is that C is equal to 2 minus 10 minus 1, 6 times 3, 1, that's 16 and minus 9. And then if we work out 16 V1 minus 9 V2, then yeah, it seems this works because that's also 3, 1. So we have a match. Right, so now let's do a very slight twist to what we've been doing. So now suppose we have bases that are not for all of Rn, but just for subspaces. So let W be a subspace of dimension k. So k we assume is less than n. And now suppose that we have a basis for the subspace that consists of the vectors ui. So in this case, how do you find the expansion coefficients? So everything works almost exactly the same. It's just there's one slight twist here, which is that we need to solve. So our task is to solve B1 U1 plus Bn Un is equal to x. So it looks very, or k. It looks very similar to what we did before. So we have a linear system whose columns again are the vectors so it looks like this. So we set U to be the matrix U1 up to UK. Now the issue is that U is it's an n by k matrix. It's not a square matrix. So U inverse does not exist. So instead, what you need to do, you solve UB equal to X using Gaussian elimination. So you form the extended matrix UB, and then you row reduce until you get, and now since you have a rectangular coefficient matrix, you're going to get zeros at the bottom. So you get some 0 rows at the bottom, and then at the end of the day, no, sorry, that should not be B, that should be X. So at the end of the day, you get the expansion coefficients B, they sit there, and then you get zeros at the bottom. All right, so maybe that got a little abstract, but I think everything should become much more clear if we look at a specific example. So let's look at a specific example. So now we are in the vector space R5. We are given 3 vectors, U1, U2, and U3, and they form a basis for a subspace W, and we know that X belongs to W. So if you take an arbitrary vector, then typically this will not work, but these are chosen so that X does lie in the span of U1, U2, and U3. So then our task is to solve the linear system and this we can write as okay, so it looks like this. We have a 5 by 3 coefficient matrix like this. So we need to solve this equation. We set this, so here this is what we've called U. Right, so now we want to form the extended system UB. And now there's a whole sequence of tedious row operations. I'll spare you that stuff. But in the end, you'll end up with the identity matrix here because these 3 vectors, they're linearly independent. So we know that on the left, the RAF of the leftmost 3 columns is necessarily going to be that. And then in this example, what these numbers worked out to was the following. Now notice that it's important that these guys are 0. You must have zeros there. Otherwise, you've either done an arithmetic error or this statement would be false. So the problem states that the system is consistent. So you must have a solvable system. And then here, this is the vector B. So in this case, we get the answer B is equal to 1 minus 1 and 1/2. This is the expansion of the vector X in the basis B. So what about changing basis when you're in a subspace? So suppose we have, so it's the same setup as before. You have one set of basis vectors U1 up to UK and another one V1 up to VK, and they form the basis B and C respectively. They both span the same subspace W. So now given a vector X in W, You could either expand it using the basis B or using the basis C. So the question now is the same as before. Suppose you know B, so we know we want C. So we want to solve the equation, so x can be written as UB or as VC. So UB is equal to VC, where of course U and V are the matrices whose columns are formed by the respective basis vectors. But now the problem again is that U inverse does not exist. Because U is rectangular. But so we cannot form what we did before, or V. Sorry, I've been mixing up U and V here. So V inverse does not exist. So we cannot do P as V inverse times U, but we can solve Vp equal to U for a K by K matrix P. So in other words, what we do here is that we form, so in principle everything works exactly the same. You form this extended matrix, so this is an n by k matrix, and that is also an n by k matrix. And then you start doing row operations, and you will end up with the k by k identity matrix, and then all zeros. And over here you will get the k by k p matrix, and then all zeros. And then you just read off P. So again, I think this will become much more clear if we do a specific example. And we'll continue with the same example as we did before. So we're given, so these are the same three vectors, U1, U2, and U3, as in our example here. And now we're given three new vectors, V1, V2, and V3. And our task is to find P such that the expansion of a vector x in the C basis is equal to P times the expansion in the B basis. Okay, so let's think carefully about the dimensions of these guys. So the subspace has dimension k, which is, maybe we should, why don't we, instead of k, let's write 3, since this is a specific example. So this is a 3 by 1 vector, P is 3 by 3, and that's 3 by 1. And P solves the equation Vp is equal to U. And now the dimensions here is what makes this a little tricky, because V is not square. But never fear, we form the extended coefficient matrix 1, 2, 0, 0, 3, 0, 3, 1, minus 1, 2, 2, 2, 0, minus 2, 2, 1, 5, 1, minus 1, minus 1, 1, 0, 0, 2, minus 5, minus 4, 2, 2, 2, 0. Okay, and then you do all these tedious row operations, and at the end of the day you end up with a 3 by 3 identity matrix, then the block of all zeros, and over here we got the following, and then all zeros. below the line. All right, so it's important to make sure that you get a consistent system. If you were to have something non-zero here, then either the premise of the problem is wrong or you committed an arithmetic error. So now what you have here is the P matrix. So P is 1, minus 1, 0, 1, 0, 2, 0, 1, 2. Like that. The very last thing we will do is simply to state a theorem that says that this operation of converting a vector in V into a set of expansion coefficients, it's a linear operation. And this is pretty much the definition of a linear operation. But yeah, so if you have vectors x and y in V, then if you want to form the expansion coefficients of x plus y, then it's the expansion coefficients of x plus the expansion coefficients of y. Likewise for linear scaling. So the expansion coefficients of Cx is C times the expansion coefficient of x. So once you have this, you can of course do induction, and you get that if you have a linear combination, then, oh, I forgot the sum. So the important point here is that this is a sum in V, and this is a sum in Rn. And the proof here is really extremely straightforward. It's just uniqueness. Let's maybe do it, or at least sketch it out. We'll just do A. So let A, B, and C, oh, that should have been Y. So we define the vectors A, B, and C as the expansion coefficients of x, y, and x plus y, respectively. So we need to prove that C is equal to A plus B. But now x plus y, this is equal to sum AI ui. And then sum BI ui. So here I use that. So this is because the expansion coefficients of x is A, and the expansion coefficients of y are B. Okay, now just by linearity of the sum, we get that this is sum like that. And now since the vector C is unique, here's the punchline, since C is unique, we must have Ci is Ai plus Bi. So you see we've shown that if Ai are the expansion coefficients of x and Bi are the expansion coefficients of y, then the expansion coefficients of x plus y are Ai plus Bi, and since they are unique, that must be Ci. So C is equal to A plus B. And that concludes that proof and the lecture.